Hey everyone. So the next video is going to be on Bayesian statistics. This is kind of an interesting video because these videos are being recorded for statistics courses taken at the University of Utah Department of Mathematics. And as of this date, which as you can tell is September 11th, September 11th, 2020, there really isn't much teaching of Bayesian statistics at the math department. And in fact, the main text for this class, for the Math 3070 class, really does not discuss Bayesian statistics. It does discuss Bayes' theorem, which Bayes' theorem does kind of present itself automatically as a form of inference, but not really discussing the further, going further down the rabbit hole of Bayesian statistics. This is basically, like, when I wrote this lecture, this was basically the only lecture on Bayesian statistics in the math department to my knowledge. So, consider this a treat. We're going to talk a little bit about Bayesian statistics in this video, which is certainly going beyond just the R programming part and going more into statistical method, and in fact some statistical theory, some really deep theory. The difference between Bayesian and frequentist statistics, they're not just different methods, they are different ways to think about statistics and how, not just statistics, but how science should be done. So, the methods that you guys, if you're watching these videos, I'm presuming that you're learning is frequentist statistics. So in frequentist statistics, you basically consider there being a fixed yet unknown state of nature that you are trying to learn. Perhaps you're trying to learn about the value of a parameter, and you consider that parameter to be unknown, but it is essentially fixed and non-random. So you're trying to learn about the value of that parameter using data, and a lot of the statistical theory developed with the presumption that this parameter is non-random, just unknown. So we understand the behavior of these tests because we know the distribution of the data, because the parameter itself is just it exists. And when you're doing, say, a hypothesis test, either the null or the alternative hypothesis are true. One of these things are true without any additional wrinkles in it. One of those things are true, we just don't know which. And we're trying to use data to learn which of these hypotheses are true. Right? So if we observe data that is highly unlikely under the assumption that the null hypothesis is true, the null hypothesis is rejected on the grounds that it seems unlikely, given that the data that we observed is unlikely if it were true, and thus we're going to assume that the alternative is true. And this is the school of thought that arose in the 19th and 20th centuries. The mathematician Fisher developed these methods. Student William Gossett, he also developed these methods. He's William Gossett is kind of who you kind of attribute the t-test to. He's a very interesting character. He was actually a brewer at Guinness, and he was developing statistical methods to help Guinness make better beer. And the reason why we refer to William Gossett as student is because he was developing these state-of-the-art statistical methods and developing them with Fisher, but he wasn't allowed to publish under his name because Guinness considered these methods a trade secret. So they didn't want rival brewers to know about these statistical methods. So he's published under the name Student. These methods were very popular throughout the 20th century. They remain the dominant statistical school of thought, and these are generally the methods that are taught in introductory stats courses. The alternative to the frequentist method is generally the Bayesian method. Bayesian statistics is arguably older than frequentist statistics, because Bayes and Laplace are some of the pioneering individuals in Bayesian statistics, both of them predate Fisher. And unlike, not just Fisher, also Carl Pearson. He's also one of the leading individuals in mathematical statistics. Unlike frequentist statistics, where we try to learn about a state of nature that we presume to be fixed, the Bayesians view the true state of nature as being essentially random. Now, they may not necessarily say it's random, but they allow us to make probabilistic statements about what state of nature is actually true, which, whether that means that the parameter itself is truly random or whether we're trying to think of some alternative way of viewing probability and what we can make probabilistic statements about. At the end of the day, these two methods require different interpretations on what probability means, which is its own video. I actually recorded a video about the interpretation of probability that you're welcome to watch, but that's going to be a separate topic. But they treat the parameter of interest as being essentially random, and the true state of nature as being random. So we start, before we collect any data, we assign to our parameter or to our state of nature a prior distribution, which reflects our beliefs about the possible values of theta prior to any analysis. So you may be familiar with, when talking about Bayes' theorem, talking about drugs and whether an individual has a disease or not. And, well, maybe not, let's not say drugs, but like applying tests to individuals to see whether they have disease or not. And you have a prior belief about the probability that this individual that you're about to test has a disease. So you assign a prior distribution, a prior probability to that belief. And then we collect data, which, going back to that example, corresponds to conducting a test on this person to see whether they have a disease or not. And after you collect data, you compute a posterior distribution, which reflects where you believe theta, where you believe a parameter is, or what the true state of nature is after you have observed data. So what you end up with in the end is a probabilistic statement. You say, now the probability, after having assumed this data, of this thing being true is some other number. So this is going to be the case with the hypothesis testing. You basically say that you never really reject a hypothesis in Bayesian statistics. You merely say that one hypothesis is more likely than another. You assign probabilities to different hypotheses. So that means that the Bayesian mode is entirely different from the frequentist mode. With the frequentist mode, you have truth or untruth. With Bayesian thinking, you have varying degrees of truth. You have probabilities of things being true. So Bayesian methods are heavily reliant on Bayes' theorem, which I'm displaying here. So we say the probability of a hypothesis given the data is equal to the probability of the data given the hypothesis times the probability of the hypothesis divided by the probability of the data. The thing with all of that discussion, though, is that's so when writing stuff down like that, this part right here, you always know that you have to divide by the probability of the data itself. So often what's written is the probability of the hypothesis given the data is proportional to the probability of the data given the hypothesis times the probability of the hypothesis. This symbol here, I don't really know what to call it. Almost like 3/4 of an infinity sign. I don't know. But this symbol means proportional to, meaning that two things are equal except for a multiplicative constant that is non-zero. And also we're going to say positive. So if yeah, this is basically Bayes' theorem. It's just you write this without dividing by the probability of the data because you know that in the end you have to do that. So we decided that the normalizing constant is uninteresting to the key ideas of Bayesian statistics. Now that said, if you're doing Bayesian inference, you do need to compute that normalizing constant, and one of the disadvantages of Bayesian statistics is that computing the denominator is actually quite hard. So computing that constant that you need, because this is not going to result in proper probabilities. It's not going to actually result in probabilities that sum to 1. So you need to divide by some constant, which corresponds to the probability of the data, in order to be able to make truly probabilistic statements and be able to actually do some form of inference. And doing that is actually quite hard. That's one of the reasons why, in many ways, Bayesian statistics is the disadvantaged statistical method. It's because you need to compute you need to compute often something that's rather difficult to compute. In the end, This probability, the probability of the hypothesis given the data, is going to be the a posteriori belief that H is true. Or it might be a distribution, like a probability distribution. So I would say that Bayesian methods, there is increased interest in Bayesian methods. Part of the reason why is I hope I haven't come across as really just trashing Bayesian methods in this conversation, because there are some things that Bayesian methods do very well. Bayesian methods give an elegant way to update beliefs given additional data and what you should be currently believing. The idea of a prior and a posterior distribution, those, like the prior distribution is somewhat uncomfortable because often the prior distribution can involve some degree of opinion. And if two individuals with different prior distributions are going to have two different views of the same data set, and that's disconcerting. But one nice feature of Bayesian statistics is the ability to update your beliefs, because after you have rejected the prior distribution, after you have computed the posterior distribution, that posterior distribution will become the new prior distribution in any future analysis. Or at least that's ideally what would be the case. The difference between Bayesian statistics and frequentist statistics, there are many different differences and arguments one way or the other. This is basically a holy war in the statistical community, which one to use, one or the other. The differences range from philosophical to computational, and I'm just going to leave that debate aside. I am going to, though, discuss some Bayesian statistics with you because, I mean, they are more common and they are nice. So let's go ahead and talk about them. Let's consider a very simple example. This is, this is, in a way, I don't think analysts actually do this, what I'm about to show you, but this should give you an idea of how Bayesian statistics work. So let's consider an example. We believe that our data is coming from a Bernoulli experiment. In other words, you're flipping a coin and you want to know the proportion that times the coin lands heads up. So your data is following a Bernoulli distribution with a parameter p, where p is probably the coin lands heads up. The thing is, in Bayesian statistics, we're going to treat this parameter p as being essentially random. So we're going to first assign a prior probability distribution to the parameter p. We might say, for example, that every p between 0.05 and 0.95, incrementing by 0.05, each one of those p's are equally likely, in which case all those p's are going to have a probability of 1 over 19 of being essentially true. This is our prior probability distribution for the parameter p, and this is known in Bayesian statistics as an uninformative prior, since you're saying that all p's that you are allowing are equally likely. So after we have assigned this distribution to our parameter p, we then collect data from our coin by performing n flips and counting the number of times the coin lands heads up. We'll say that that the number of flips is s's. So we need to compute what's known as the likelihood. And going back to this formula for Bayes' theorem, this part right here, the probability of d given h, is known as the likelihood of the data d given that h is true. We need to compute that likelihood for the data. So to compute the likelihood, we do so like this. We compute the probability that we get s heads out of n flips, given that the true parameter p is p naught, and that's going to be proportional to p naught to the power s times 1 minus p naught to the power n minus s. You may recognize this. This looks a lot like the probability mass function for the binomial distribution, but it's missing a constant. It's missing a multiplicative constant. Well, we're going to just basically neglect that for the moment. So after you have combined this likelihood and the prior together in Bayes' formula, you end up with a formula for the posterior distribution. So the probability that p is equal to some quantity p naught, given that you observed s heads out of n flips, is going to be proportional to the probability of seeing S heads out of N flips, given that P is equal to P naught, times the probability that P is equal to P naught. This is the likelihood, and the part that's now actually highlighted is the prior. And that's going to be proportional to P naught to the power S times 1 minus P naught to the power N minus S times the probability that P is equal to P naught, which we've said is 1 over 19. So this is going to be proportional to the posterior distribution. Here's the thing, though. If you add up those numbers for all valid P naught, which are going to be numbers between 0.05 and 0.95, incrementing by 0.05, so 0.05, 0.1, 0.15, and so on. If you add up all those numbers, it doesn't actually add up to 1. So this is not actually a proper probability distribution. This constant that it adds up to is not equal to 1. That said, after you've computed the posterior distribution, you could hopefully compute this constant in order to normalize this quantity appropriately. So then you would have a proper posterior distribution that could then be used for inference. So in general, this is actually rather difficult to do, but given the way I've set up this problem and the fact that we are doing things in R, it's actually not going to be that hard because we're just going to use the sum function. All right, so let's go over here. I wanted to use those notes because, well, I mean, we really need to see the math rendered. All right, but anyway, now let's get to our R session. So I'm going to create a function called the plot PMF function. This is a function for plotting probability mass functions. Okay, so you can just read through that code if you're curious on how that works. I'm not sure if I think I did use this function in other videos, so it's the same function from before. I'm going to change my plot settings. Let's promote this. Okay, so change how we're making our plots. We might actually change where the plot appears. Anyway, so now let's go ahead and consider our prior distribution. Well, first off, the possible values for P are going to be numbers between 0.05 and 0.95 incrementing by 0.05. So here you actually see the possible values for P displayed. So we say that any one of those numbers are possible. The prior distribution of P is going to be the number of possibilities divided by, is going to be 1 divided by the number of possibilities. So this is what we end up with for our prior distribution. This is basically 1 over 19. And if we were to plot the prior, this is what we would get. Plot new, figure margins are too large. Okay, so we need to actually promote this and try this again. Okay, there we go. So that's our prior distribution. Let's suppose that we flipped a coin 20 times, and then out of those 20 flips, we observe 12 heads. So now we need to compute our likelihood function, which is going to be proportional to p to the power s times 1 minus p to the power n minus s. So this is going to be our likelihood with up to a constant. Okay, and then after we have the likelihood, we can start to compute our posterior distribution by multiplying the prior with the likelihood function. So after we do that, here's the thing though, the posterior as it is currently isn't actually normalized. It's not a proper probability distribution. So we're going to divide the posterior by the sum in order to have something that actually is a probability distribution. Now we have a bunch of numbers. You can't really tell what those numbers are saying, but if you were to plot it, okay, now we're actually cooking. This is actually something of interest to us. So now we have a posterior distribution describing what we believe the true probability P is. So notice first off, notice the shape of this distribution. It's centered around P equals 0.6, which just happens to be the sample proportion of successes. So that is the single most likely number for P, which in Bayesian statistics is referred to as the maximum a posteriori estimator. Or estimate for P. So in this case, the single most likely value for this parameter P is 0.06, which corresponds to the sample proportion, which makes perfect sense. That said, we can use this posterior distribution to make a number of interesting statements. For example, if we wanted to determine whether this coin is biased in the favor of heads or not, we could actually compute the probability that this coin is biased by computing the probability that the probability of getting heads is greater than or equal to 0.5. So the probability that the coin is the probability of getting heads is at least 0.5 is going to be 0.867. The probability that it's less than 0.5 is going to be 0.13. So we read that thinking that basically now we have two possible states of nature, that the coin is maybe super fair and that the probability of getting heads is at least 0.5 or 1/2, and we have the probability that the coin is less than fair. So if you're thinking of a game where you win whenever you get heads or not, and what we observe is that the probability that the coin has the probability of getting heads of at least 1/2, that's 87%, which means that it's quite likely that this coin has a probability of seeing heads of at least 0.5. Now that said, it doesn't necessarily mean that the coin is not that the probability of getting heads is less than 0.5. That's unlikely, but it's not necessarily impossible. 0.13, a probability of 0.13 is certainly that's an event with that probability is certainly possible. Okay, so that's how hypothesis testing would look in a Bayesian framework. Another thing that we can do with Bayesian statistics is compute what are known as credible intervals. These are the Bayesian equivalent of a confidence interval. So a credible interval is going to be let's see. Let's actually go over here. Okay, so a credible interval is an interval such that the probability that this parameter is in this interval is equal to C. So that actually sounds like what people want to say for confidence intervals. You want to kind of say the probability that this parameter is in the confidence interval is C, but that's actually not true, right? That's not how you interpret confidence intervals. If only because for confidence intervals, which are frequentist constructions, this parameter P is not random. So it either is or isn't in an interval with probability 1. Right? So we just don't know which is the case. But in this case, when we're treating this parameter P as being random, we genuinely can say that the probability that this parameter P is between A and B is our probability C that we specified. So the trick with this situation is that when trying to compute a credible interval here, we are dealing with a very discrete distribution. So if we wanted a 95% credible interval, we can't actually get it because of the discrete nature of P. We have forced P to be discrete, which is a little unrealistic. A real Bayesian would not actually describe P in the way that I have here. I have only done this for the sake of simplicity. A real Bayesian would be saying that the prior distribution of P is some beta distribution and blah, 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 blah. So that would not actually be a problem in a real, in like actual Bayesian statistics. But here that is an issue that we can't actually get a credible interval of 95% just because of the discrete nature of this distribution. So what we're going to do is find an interval such that the probability that this parameter P is in this interval is at least 0.95. So probably going to be larger, but as small as it can be. It's as small as it can be if it's not 0.95. So in this case, we end up with two boundaries for our credible interval with this code. What we're basically saying is that the lower bound of this interval is going to be 0.35 and the upper bound is going to be 0.8. And the actual probability of being in this interval is going to be 0.989 or about 99%, which basically means that there is a 99% chance that the probability that this coin gets heads is between 0.35 and 0.8. So, all right then. So that's the conclusion of this lecture. And I wish you all the best, and see you later.